So next speaker is Randy Turner. Randy works at SFEI also, San Francisco Estuary Institute. And you have an environmental science degree from UC Santa Barbara, representing now, I think, the full UC system today.
Close to it, yeah.
Oh yeah, Merced. We didn't get Merced. Yeah. So anyway, thank you very much for coming to speak, Randy. And okay, so thanks.
Well, I feel better now having one of these water bottles after that last talk. So let me grab all the tools here. So we're going to continue on that cyanobacteria trend after Karen's comment. I'm working on a really interesting project using satellites to try to get a different picture of what cyanobacteria trends are occurring in California. Betty gave us a nice little background a little earlier. Basically, if there's water, light, and nutrients, you're probably going to find cyanobacteria in some degree. But you give them enough nutrients and nice slack water, it tends to cause algal blooms. And the cyanohabs term is used in that regard. Obviously, some negative impacts when blooms can get to really high levels. But the thing that I think most of us are worried about are more of the toxins that are produced by some of the cyanobacteria species. So with that said, SWAMP has contracted with the San Francisco Estuary Institute so we can look at some of the data from some satellites in partnership with NOAA and really get a better understanding of what those public health risks are. So with that, we've developed the database and GIS infrastructure to process and analyze that satellite imagery. We have historic data, about 10 years of data from the MERIS satellite that we'll be looking at and trying to develop a status and trends update. And then another satellite, a replacement satellite, was launched in February. It's still under the commissioning process, so it's not active yet, but it'll be roughly comparable to MERIS. So we're looking forward to that, having that information come back in near real time. And as far as we know, the algorithms and the processes that give us the right information, it should be roughly equivalent. And so we're hopeful that, as soon as that data starts reporting, it'll be usable. Speaking of reporting, we'll also have a web platform that will be passing off to SWAMP so people can look at that satellite imagery, look at all the data related to it, as well as comparable data within CEDN. And we'll use that information to reach out to water body managers and public health officials to give them information about blooms and trends that are occurring, as well as issue some information to the public in the form of bulletins and newsletters. So we'll do the 800-kilometer view rather than 30,000-foot view to really cover this briefly. The satellite flies over. It's kind of like when you're out mowing your lawn, you're not following that same path each time. You're going to kind of overlap a little bit. So over 1,000 kilometers wide is the view, and we get data for each pixel of information is about 300 meters on a side. So from nosebleed seats to nosebleed seats, we're even going to include the whole Oakland Coliseum as well as some of the parking lot, just as a reference. And that pixel will basically be kind of the average concentration for that whole area. I'm not the person to really go into the details here, but lights, some lights absorbed by algae at different concentrations, and that light that's reflected back up to the satellite, they're able to look at that in different portions of the light spectrum, and within each of those bands, it'll basically be able to tell you what's the total algal biomass. And the beauty of the MERIS satellite is it has some key bands in the phycocyanin or in the near infrared that's able to tell what portion of that algal biomass is from cyanobacteria and what's from non-cyanobacteria. So we're able to generate 3 different data points for each pixel of information. Again, this is telling us how much cyanobacteria is in there, not it doesn't tell you how much cyanobacteria that is a species that produces toxins. So we're being general here, and it is not a measure of toxins. So we don't have this direct relationship to some of the public health thresholds that are out there. So that's the unfortunate part, but there's still a lot of really great, useful information here. When we look at kind of a daily image, this is of Lake Erie where a lot of the pioneering work was done. You can see kind of the heat map approach there. Red is bad. So for any one day, it's going to tell you some information, but wind is going to blow the algae around. If a cloud shows up, you're not going to get any information. It turns the lights out, so to speak. So we don't want to rely on a daily image too much. The approach that's been pioneered by NOAA is to take all the images that you get within a 10-day period of time and generate a maximum composite of that. And because we're kind of pushing the edge of the envelope of smaller water bodies, to get a quality image, we're trying to look at a longer time period just to see if we can tease more data out of this. So we're kind of testing a slightly modified approach of a month-long composite. So again, for a 10-day period of time in this example, there were 7 times the satellite flew over California, but 2 of those times it didn't fly over Clear Lake itself. So there's no data for those particular days. What you have is the individual pixels you can see. The nice part is the pixels are always in the same locations. So what you can do is for each of those pixel locations, you take all the images and you take the maximum value from each location, and that's what builds your 10-day max composite. And for the 10-day composites, we do it as a running average. So it's today and the previous 9 days of images, and then tomorrow and then those previous 9 days. In terms of quality control, we want to have more than 17 pixels within each composite image to really feel that it's statistically valid. And what we're able to do is output the data in a few different metrics. We've chosen to use an estimate of microcystis cell concentration in cells per milliliter. There's some pros and cons to that metric, pros and cons to the chlorophyll A metric. For now, we're choosing this, but we could report in different avenues. And then within each of those composites, we want to generate kind of an estimate for the whole water body of what that mean concentration is, the median, and then probably most importantly, the 90th percentile of the max. So in this case, you would throw out some of those deep red values for the lower portion of Clear Lake, but you're still going to end up with something that's fairly red in this case. So the numbers up there, you can see, the mean for this particular value is 125,000. The median would be 186,000, but that 90th percentile is 1.6 million cells per milliliter. So a big difference between those three calculations. And so from a public health perspective, if I'm going for a swim in the lower portion of Clear Lake, I don't care about the mean. I want to know what's really the public health risk there. And at this point, water body managers will typically close a whole water body or post a whole water body and not post specific portions of a water body. And if I were to go out and collect a grab sample, I'm going to look for where the bloom is and sample there. So that 90th percentile is more similar to how we've traditionally collected samples, and it's also going to be more protective of public health. Unfortunately, though, these types of numbers don't relate at all to the thresholds like I talked about before. There's one reference in the new California public health thresholds that's 4,000 cells per milliliter of a toxigenic species of cyanobacteria. So, orders of magnitude below what we really are talking about here. And then the satellite background level, it can't read anything below 10,000 cells per milliliter. So we have a limitation on how we can use this. What we're doing at this point is we want to have some comparisons to thresholds. So World Health Organization has a few of 20,000 cells per milliliter and 100,000 cells per milliliter as something we can compare to. But again, the values that we're seeing even in this one example can be much higher than that. So we've created a 1 million cells per milliliter threshold as well, just for comparison purposes. And we're following that color-coded approach that everyone seems to be loving. In general, we want to hope that things are green. But really, this is to understand as we put things into these bins, what are the exceedances? How often do they occur? How long do they last? In the reference of what we're trying to evaluate here, we're looking at 255 water bodies across California. So, at any one given time, how many of those water bodies are in bloom? We'll take a little dive into San Luis Reservoir just to look at some of the data sets, and then we'll look more at some regional and statewide assessments. Again, we're just getting into this data, so please don't cite it at this point. We're not published yet. And working with NOAA, we've talked about a plus or minus 15% uncertainty to all this data. So I've included some specific numbers in these graphs, but please understand there's some wiggle room here from the satellites and the uncertainty. So this is a 10-year time series. Yeah, the numbers are pretty legible. So, we can see in most years, we see estimated cell concentrations getting above 500,000 cells per milliliter. So, fairly high, with a few getting up towards 2 million cells per milliliter for the lake-wide mean. If we look instead, considering that we are talking about that 90th percentile value is perhaps more important, we see it's much higher. So, and I think an important piece here is at the very top of these values, you can see it kind of flatlines a little bit. That's because the satellite can't measure anything higher. So I think that's just a little bit important to consider. So we can see that the length of the blooms is extended when compared to the mean, as well as that overall peak. We can also, and I can't see this at all, but there's a little bit of green in there. And the green represents that non-cyanobacteria component in this stacked chart. So really what it's trying to say is, yes, there's some other algae that are there that are non-cyanobacteria, but they're relatively minor compared to the cyanobacteria, especially when you are undergoing a big cyanobloom. If we plot all the years separately on the same chart, it's pretty busy. But you can still see some general trends of, blooms starting in the spring, tapering off a little bit, and then really picking up in the fall before dying down in the winter. If we take all that data and then push it in and generate an average min-max, it's a little bit cleaner to look at, and that those trends are fairly consistent. You see that springtime and then again in the fall. So that's just a little bit of preview of some of the data that we were looking at for individual reservoirs in our status and trends report. We're going to go into about 20 water bodies that are of particular concern or importance and try to give a real detailed view of those water bodies. But we can't do that for all 255. So we'll do some other summary data and regional estimates. So I'll talk a little bit about our water bodies for our friends to the south. 7, 8, and 9 is kind of San Diego, Orange County, Riverside, I think. And the ones I have circled there, Lake Henshaw and Lake Sutherford in eastern San Diego, they're relatively small, but not terribly small. And I'll focus on those in the next slide. So I mentioned data quality and being able to have enough pixels of information to really tell the story correctly and accurately. If we don't have enough pixels, we really can't use that data according to the information we've gotten from NOAA of how to make sure this is usable. So the green is good, and that's when we have enough pixels. So Lake Henshaw was only slightly bigger than Lake Sutherland, but partly because Lake Henshaw is a little bit rounder, we're going to get more pixels showing up in open water and not on the shoreline. If a pixel is on the shoreline, we have to throw it out because that data won't be returned with just open water information. So what we see is Lake Sutherland has absolutely no months that give us good data. And the data moving forward here are all those monthly composites that I talked about. So out of the 118 months the satellite was alive and kicking, we got nothing really that fits the NOAA standards for data quality that we can use for Lake Sutherland. But there's quite a few water bodies that give us good information. I think in our initial idea of including so many water bodies, this 255, we probably overshot a little bit. There's quite a few that we're just not getting good information from, but we still have data, and we'll still try to use it for what we can, but we have to be careful and not be breaking too much ground here. So focusing on the areas that are in green, we'll look at how they are relative to the thresholds I just talked about. Red is over 1 million. So we can see in this one, Lake Elsinore, which is definitely known to have a lot of cyanoblooms. Over half the time, those monthly composites are over 1 million cells per milliliter. So not good. We also see Marina Reservoir also has quite a bit of the red, but we don't have much data for it. So even though the total number of months over 1 million cells per milliliter isn't that many, relative to the amount of data we have, it's actually almost as bad as Lake Elsinore. So it definitely hints that we need to find other ways to look at this data so we can really tell a better picture of for all those months that are technically not available. So I don't know if a lot of lakes on here to look at. Salton Sea, believe it or not, is pretty clean. We're not seeing cyanobacteria to speak of at all, despite I know it has some history of algae blooms and a lot of other issues. But so it's definitely interesting. If we look at data at the statewide level, again, I'm going to talk about these monthly composites. We're going to follow the same approach we had on the bar charts before of the color codes. Pretty difficult to see. Lake Elsinore is this bad one right there. We have Owens Lake in the Eastern Sierras isn't very good, but we see a lot that are white, and these are again the ones that are we just don't have much information for. So at this point we can't tell a whole lot about those. If we start to get a little bit more creative with our data or lower our pixel threshold, we'll get more usable data out of those lakes. But again, we have to be careful about that. But we can work with individual water providers and share the data, and they can interpret it as well. So this is Southern California. We'll go to Central California. Again, just a big overview. A lot up in the Sierras that are a lot of white and not a lot of data reporting back. Likewise on the Central Coast and near the East Bay, and some of the water bodies that we know have blooms based on field data, but they're just too small for our satellites. And then we can jump up into Northern California. One thing we do see are the water bodies that are big enough that we know have a history of cyanobacteria. We are seeing the satellite data corroborate pretty well up in the Klamath River and then Upper Klamath Lake. We see a lot of the water bodies in the far northeastern portion of the state do have some blooms, and I think if I back up, even Lake Tahoe has a signal that was surprisingly, there was some moderate blooms there. We're still trying to figure that out, and I'll touch on that in a little bit. So if we talk again about how much data is really available following that pixel threshold, roughly 150 of the 255 water bodies over the course of the 10-year data set, we get roughly 150 that we get usable data back for each month, and those are going to vary month to month. But there's a slightly increasing trend. Some of that relates to some improvements in the data transmission rates, during the course of the satellite's life. So if we focus again on just the green, we'll see the thresholds in a different way. And what we see here, which is interesting, is the area of orange, which is that between 100,000 and 1 million cells per milliliter. That seems to increase fairly substantially over the period of record. And again, this data was not during the period of time that we're kind of still hopefully at the end of, the 5-year drought. And I hope to say it's 5 years. Maybe we'll get a great winter next year. So this isn't really, during the extreme drought period. So I don't want to read too much into, environmental conditions, but just thought it's important to point out. If we take the same data from the last one and just take annual averages, we'll see that same Same thing here in a kind of a stacked line chart, where you see a slight increase in the greater than 1 million, but the vast majority of the increase is in that 100,000 to 1 million cells per milliliter concentration. But it's important to also look at information seasonally too. So if we take all the years and put it all into, look at all the Januaries together, all the Februaries, we will see for the highest concentrations of exceedance, we will see, that kind of late summer, period of time where the most water bodies are in bloom, which seems to make sense. But interestingly, it's December and January where we see the most number of water bodies that are exceeding that 20,000 and 100,000 cells per milliliter threshold. So that was definitely a surprise, and we'll have to look into that a little bit more and try to find out why. So, there's some interesting stuff that we're seeing here, but there's, some things that we just have to be careful of. Satellites they're not perfect here. Anytime there's a cloud, it's like turning the lights off. We get nothing in return. I think it's important to think of this as a screening tool. It's not gonna, compare to those harmful algal bloom thresholds that we've talked about for protection of public health. And these really are estimates. This is very difficult to compare it to a grab sample that is sent to the lab, and you run the ELISA test and you get back a number that has a regulatory importance. It's very difficult to compare that. So, plus with, the uncertainty factor here, we want to consider this, it's good information. And again, this is, estimating even the non-toxin producers. So there may be a bloom in a water body that's really, a high concentration, but if it's of a non-toxigenic species, then we don't have to worry about that particular portion of the public health risk. And again, not a measure of toxin. So one of the pieces of feedback we've gotten from NOAA is they don't have a ton of confidence in some of the lowest values. Just the satellite has a real hard time discerning just very subtle color differences, when the bloom's really not kicking. So, so we want to be a little bit more careful with that data. Luckily, that isn't the type of data that's of the most importance to us when it's really a bad bloom. So, but we just want to be careful about those lower values. We do see some false positives in the data. These would typically be really brief spikes up and then dropping way back down to, something more continuous. It's usually pretty evident when we look at the data visually on those time series charts, and what we can do is we can go back, and it's probably like one set of data, where there was just a real bad spike and then it disappears. And so we have to call that out. But we do see some false positives, and there's some other points of interference I'll mention in a few other graphs. Right now, again, this is for large lakes, but there is some work being done with some other satellites to try to develop similar algorithms that will be used to really, dial down not from a 300 meter pixel threshold, but a 300 meter threshold to more like 20 or 30 meters using Landsat or Sentinel-1. So there's definitely some improvements coming if the science can, get dialed in and everything calibrates properly. So with all the things it can't do, there are some great things that we can get out of this. We can see trends occurring, and we can see relative concentrations. So there's a lot to learn from that 10-year data set. When we look back at this, this data is going to be really helpful to understand, what's driving blooms, what kind of changes have happened in the watershed, what kind of management actions have happened. If you're a water body manager and you've applied an algicide, you can go back to this data set and say, oh, well, yeah, there's the bloom. We'll see it spatially, and then we see in the next month, it's gone in that bay or cove, but it's still present in the other water bodies. So it'll help confirm whether management actions have been helpful or not. In the end, we probably can't get data for all 255 water bodies, but roughly about 150. It looks like we're getting some usable data each month. So that's definitely a huge improvement off what's happening now. Again, as we move forward with the satellite that's just getting ramped up, we're going to use this to report back to public health managers and water body managers about what's happening. So we'll be able to give them information about the spatial extent, the concentrations we're seeing, and it'll help guide event response monitoring. So that's something that's probably one of the most important factors here. Most of that I just mentioned. So if you are one of these people in the bottom 3 bullets, please get your information to Bev, because she is helping develop the contact list that'll automate the emails that will go out to folks when we believe there's an issue. So Bev, raise your hand. Everyone should know Bev by now, but so go talk to Bev, please. So, there's some further things we really need to work on. The testing of this has been done in the Great Lakes, in Midwest, and in Florida. But California is different. We're seeing all those hits up in that northeastern portion of California. A lot of some of the eastern California alkali lakes, are those real or not? We're not sure. We need to look at what other data sets are out there to confirm whether there's blooms occurring or not. Owens Lake has some really high hits, but we know there's halobacteria that are present there. And so, is that interference? We're still working on that. And then the Lake Tahoe that I mentioned, the water is so clear, maybe that's causing some interference. We know that, the satellite typically reads about the upper meter of water. And so does that let it go deeper and give us this false baseline, this false higher baseline? We're really not sure, but it's definitely an interesting piece to look at. That was the one lake I was picking, like when I'm looking at this data and I'm like, okay, I want to go to a clean lake and see what a clean data set is. And I was like, wait, no, that can't be it. So the good part is, the raster data that we're getting from NOAA is available. And we hope that you'll ask for it so you can use it and compare it against the data sets that you have. Give it to grad students, give it to folks who want to dive deep and compare it against, against other data, against weather, precipitation, what's the local geology, what's, is your water body through a 3D listed for, for what is a bloom driver. So there's a lot of ways that this data can be used that'll complement, these existing grab samples and other data sets that you've had. So with that, I'll leave you with a nice picture of Lake Erie. Questions?